Hello everyone. In this video I shall be discussing coffee cup calorimetry and the method we use graphically to account for some of the heat loss to the surroundings. Normally when we use a coffee cup calorimeter, the basic method would be to use a mercury thermometer, which is not the case in this diagram, but normally we would use a mercury thermometer to determine the initial and final temperatures of the solution only, and that's the temperature rise that we use in this equation here, delta T. The major source of error in this setup of apparatus, the coffee cup calorimetry, is heat loss to surroundings. We can account for some of the heat loss to surrounding to produce a much better or a much closer value to the theoretical value for the enthalpy change of reaction. This can be done by using a temperature sensor instead of a mercury thermometer, which can be connected to a data logger. The data logger will log the temperature of the solution before, during, and after the reaction is done versus time, as seen in this graph here. The final graph would look something like this. It's represented by the white line. Normally we would place the temperature sensor in the solution and allow it to stabilize because there would be some initial fluctuations in temperature. Once the temperature has stabilized, the solutions are mixed in the coffee cup calorimeter, and they start reacting together and produce heat. In this case, I'm using the example of an enthalpy change of neutralization reaction, which is exothermic. So initially we would place the acid or base in the coffee cup calorimetry. For example, we place the base in the coffee cup calorimeter, and then the acid is added to the solution once the temperature of the base stabilized. Once the acid is added to the solution, an exothermic reaction starts to take place and heat is released to the surrounding water or the surrounding solution. Thus, a temperature rise would be observed, a gradual temperature rise, as long as the moles of reactants are reacting until one of the moles of the reactants is done, which is consumed, which is the limiting reactant moles. The reaction ceases. And no more heat is being released to the surrounding solution. At this point, normally this is the temperature we would determine as the final temperature using a mercury thermometer. Thus, the mercury thermometer would normally give me this initial temperature prior to mixing the solutions, and this final temperature here, which is the highest temperature reached during the reaction. Using a temperature sensor, you can still log the temperature versus time as the reaction proceeds, even after the reaction. So once the reaction ceases to occur and is complete, the mixture will start to cool, as seen by this cooling curve here. Any graph with the x-axis being time, the slope of such graphs represent the rate. Thus, during the heating curve of the reaction, heating part or heating curve of the reaction, the slope here is a bit slanted due to the reaction taking place gradually and heat being lost to the surroundings during the reaction. Once the reaction stops, the heat loss to the surroundings continues, and thus the temperature starts to drop once again. We will assume when using this graph that the rate at which heat is lost during the reaction equals the rate at which the heat is lost during after the reaction, once during the cooling curve or within the cooling curve. This assumption is written here. The rate of heat loss is assumed to be uniform throughout the experiment, although it might not be, since initially the temperature is higher, so the heat loss to surrounding might be higher than when the temperature is lower. But we will assume that the rate of heat loss during this part of the curve equals the rate of heat loss during this second part, the cooling curve of this curve. Once the cooling curve is obtained, the data logger can be stopped. To account for heat loss, This cooling curve is normally extrapolated, as seen here by this red line, is extrapolated, and the temperature rise is determined from the initial point of mixing of the solutions up to this point here. This is your final temperature without any heat loss. This point is normally not determined like by reading the y-axis here. It's normally determined using the equation of the straight extrapolated line here, which would be given in the question. Thus, let's say the mixtures were mixed together at 100 seconds, and I want to determine this point here, the temperature at this point here on this extrapolated line. I would therefore substitute 100 seconds as x, and the slope and the y-intercept would be given, and thus the temperature, the final temperature with no heat loss, can be determined. This line, this temperature rise would represent the temperature if the reaction had no heat loss to surroundings and was an instantaneous reaction, thus increasing the temperature rise. If the temperature rise were to be increased, because if as seen here, if we were to use a mercury thermometer, this would be my final temperature, and thus the temperature rise would be somewhere around this high. While on the other hand, if a temperature sensor is used to plot the cooling curve and extrapolate the cooling curve, this would be my temperature rise right here. And higher the delta T, the higher the delta T in this equation, as seen here, the higher the temperature rise, this will directly increase the enthalpy change of reaction and thus produce a more reliable value which is closer to the actual literature or theoretical value. You will get such questions in an exam in which they use the temperature sensor instead of a mercury thermometer, and the extrapolated line would be drawn. And the equation of the line would be given. Thus, if you were to calculate the heat released by this reaction, excuse me, with no heat loss, I would have to determine the temperature rise as the initial temperature would be the initial point of mixing, and the final temperature would be at the same time of mixing, but on the extrapolated line right here. And this is the delta T that would be used to account for heat loss, thus producing a higher enthalpy change of reaction. I have attached a worksheet, which is one question regarding this concept of accounting for heat loss for enthalpy changes occurring in reactions. Please complete it and send it to me by midnight tonight. Thank you for watching.